what should be our approach? I think here is what little bit some trouble will come. We don't have any exact the formula here. So therefore, to overcome this particular situation, to get an expression for potential energy, I am going to introduce to an idea called as a gravitational potential. Through gravitational potential, I can write interaction potential between the bodies or between the body and particle. See, like why I'm studying this also very important in physics. First of all, what is the idea of energy? Why the idea of energy has come into picture? Because to minimize mathematics. And we can understand the system. No? System will expand or contract, will shrink, all that. The overall broad aspect of the system, what happened, the energy will give. So therefore, so definitely I want to make it still more stronger, this energy aspect. So therefore, for body and particle, between two bodies, what is interaction potential? For that purpose, so what happened, I'll introduce one more idea called as the potential, gravitational potential. Okay, got this. So first again, I'll define the gravitational potential for a point mass. Okay, time being we can't use the formula. Any reason why we should not? Because m1 is not a point mass. See, you read S.C. Verma. Why we suggest S.C. Verma book is, sir, what is their simple problem? Okay, leave problem. Okay, if you are very good in numerical, but read the theoretical ideas. No, is trying to build up students like why you are studying this, why you are studying, why the potential you are studying. It's not like something where you take some book and solve numerical. Why you are studying also very important, no? And you'll try to build up a link so that what happen, student will not to just gather information. What all you feel is I'm studying for this purpose, and it become a very good memory. When you read S.U. Verma, it will not become a forcible memory. You'll enjoy a subject, and automatically you're going to remember it. When you read other books, know what happened? Information is forced on you. You feel like that, but S.U. Verma not like that. It will graduate. You will build up like a story. So when you listen story, will you forget? Will not. So the same thing happens with S.U. Verma. The content which is there, no, it will build up a story. That one. A student must have a patience to grasp that ideas which are hidden in the book. Okay, now gravitational potential I'll bring in. So there's a question mark, not a point mass. Okay, now I'll introduce to the idea of gravitational potential. So I'll directly let me define it. At a point is defined as work done by external agent in slowly moving work done per unit mass. Work done per unit mass by an external agent in slowly moving from infinity to that point. At a point is defined as work done per unit mass by an external agent in slowly moving from infinity to that point. What is in slowly moving? Unit mass There's a one definition is what in SURMA is giving. So same thing I've just picked up here. So let me take a point mass. And it's a fixed here. Okay, there's an extra agent. And he'll be holding that test mass, or you can call it a point unit mass. And he'll move slowly. So initially where is at infinity. Finally what will happen? He will come to the so when the test mass is here, how he'll move? He'll move very slowly, step by step, step by step, like this. He will never have any acceleration. In that way, what happen? He'll move that one. M naught you call. The test mass is what? M naught. So now what happened? We are is at a distance now at point P. What is the gravitational potential at point P? We'll define it. So what is the basic formula? Work done by extra agent in moving a test mass from infinity to point P per unit test mass. Unit mass or unit test mass, anything you can put. So what is work done? So what is the force that is acting? So when it is moving, I think some attractive force is acting, no? Here. And it will undergo a displacement dr. So what is the work done? So this should be equal to F into dr. From where? From infinity to r. So this should be equal to what is the force of interaction? Gm m naught r square dr by m naught. M naught get cancelled, so Gm will be outside. This should become equal to Gm minus 1 by r infinity to r. So what is the gravitational potential at point P? Minus Gm by r. This is due to point mass. Sir, like what is this m naught? I'll call it as a test mass. What is the test mass? It will not produce field of its own. And what all we define potential, it is due to the point mass here. So what is the field strength at point P? Minus Gm by r. Sir, what is use of this? You can see that one. It's a potential which will help us a lot in numerical than the field. Because I would say whenever a field is conservative, we can define. So what is this? Potential. What are the features? It's a scalar quantity. It can be positive or negative, but it's a scalar quantity. That's the one thing. Next again is defined only for conservative fields. There's one more condition is putting. Okay, like this, what happened? The idea of the gravitational potential is introduced. So what should be the unit for this? Work done. What is the work done? Joule, joule per kg. So what is the unit for this? Work done per unit mass. So joule per kg, what happened will be the unit for the potential. It's a scalar quantity. Gravitational field is a vector quantity. Now this what potential we define for a point mass here. Okay, let's extend this. So let's calculate the potential due to what now? Due to ring, or say due to first a finite rod. Now what is the potential at a distance? Length of the rod L and lambda be the mass per unit length. There's a finite rod. at point P, I want the potential. So what is the method now? So first I'll assume a small element at a distance x. What is the potential at point P? dV is equal to minus. There's a rod I don't know, but do I know for point mass as it is? I'll assume this rod made up of such point masses. If I add up all the point mass, I'll get a rod. So what is the potential due to point mass? Minus G. What is the mass of that element? dm at a distance x. So what is the further dm? Minus G lambda dx. G lambda. So this will be x to power of minus 1 dx. No, at a where all the mass is present, at from x equal to a to a plus L. So this will be potential minus G lambda minus 1 by x a to a plus L. Negative of negative will become positive, no? Yeah. So this will be negative.
That you did not integrate it.
Oh, I didn't integrate it. Okay, thank you. This one. After integration, x to power of minus 1 plus 1, it's become infinite. You know what is dx by x? It should be log x, no? I think I'll keep it here. No, integral of a to a plus L. So this will be v equal to minus g. This will be log x a plus L. So minus g lambda log of a plus L minus log a. Okay, let x equal to a plus L. Okay, this is capital L. Now, what is this potential we are defining with respect to what? So something, say you say potential with respect to what? So let me drag you to the basic idea. I say potential at point P is minus Gm by L. With respect to what? With respect to 0. Where 0? At infinity.